All right, welcome to Computer Science 305. This is programming languages, and today we'll be talking about memory locations for variables. So really, this is just, the concept of a memory location is really just a secondary binding question, right? Before we were talking about when do we bound different aspects of the programming language. Could it be language implementation time, when the language is defined, load time, runtime, etc. But now we're talking about we have all these variables and they have a value associated with them. And essentially they have to be somehow stored in memory, right? We have to link the memory location and the value stored there with this actual variable that we're utilizing in order to really make programming work. And so this is a separate but similar binding question. And so typically we have variables that are bound, dynamically at runtime to values. And so this is the types of variables that we're talking about here are mainly local variables or method or function parameters. So the question becomes, how are we going to do this, right? And when we look at languages that we might be more familiar with, for example, Java or C, it has an inherent, these imperative languages have an inherent or maybe implicit way of understanding how this is done, right? We have an assignment. For example, here we're assigning the value 0 to A, and actually A is a representation of the memory location where that value will be stored. On the other hand, when we have a functional language, functional languages tend to hide this, right? The val A equals 0 is not an assignment, right? It's an association, a connection between that variable name and that value. It's binding the value, binding A to the value 0, right? But this is not going to change anymore after that. And so what we have to do is we have to understand how this is actually working under the hood. And so but we do know that regardless of what type of language we're looking at, we know that variables must be connected to values and be represented in memory, as we've been saying so far, right? So essentially everything is facing the exact same binding question. It's just whether or not it's implicitly shown to us or is it explicitly shown to us. So today what we're going to be talking about are 6 main things. The first concept is activation records, and this is kind of a way of understanding how memory is set up for each one of these different functions and how the variables are going to be stored. Then we talk about static allocation versus stacks of activation records. Then we look at what do we do when it comes to nested function definitions like we see in ML and other similar languages. Then we move to when we need to pass functions as parameters to other functions, and what does that mean for the activation records themselves. And then we finally get into long-lived activation records. And so this is going to be quite interesting, but first we need to start with the activation record itself. And so we need, in order to understand how we're going to do this whole allocation of a memory location for and binding a memory location to a variable, we need to understand how do we actually, how does a function represent its use of memory in during runtime in a programming language system. And so if we go back and think about the classical sequence, right, this is all stuff, a lot of this stuff is done by both the loader and the runtime under the hood, right? There's an excessive, or maybe not excessive, but a very complicated mechanism underlying every language system that sets up for every time you call a method, every time you call a function, every time you construct an object, and setting up the storage of its values and variables associated with it in memory, right? And so we actually have to have some code that does this in a, what we'll say, very efficient manner, as well as efficient in time, as well as efficient in storage. And so one of the things that we talk about is how do we know for how long do we need to like create these variables, right? And how long does this memory have to be allocated? And the basic concept is that we have this concept of an activation, right? So activation is the lifeline of a function. How long is it actively going to be in memory, and how long do we have to hold that part of memory or lock that part of memory to that function? And so we call this lifetime the activation of that function, right? And typically, activation is only going to be a lifetime of a function only starts when it's called and ends when it returns, right? But that's not always the case, and we'll talk about that a little bit later. So what we're saying here is that the lifetime of the execution of a function corresponding from when it's called to when it returns is what we'll call the activation of that function. And each activation has its own binding of a variable to memory locations, right? So for all the different variables locally defined and parameters within that function, they are a part of that activation, right? And it should be, and we call those types of variables that are local to that function, we call them activation specific in our text. But it also goes by the name of, these could be called dynamic variables or automatic variables. So if you see that anywhere else, it will, just think about that. This is, the opposite of this would be static variables, those which are defined at load time rather than runtime, like a dynamic variable. This is different from dynamic versus static type checking, but and so we just have to be aware of what's going on, right? So if I talk about dynamic variables, I really mean activation specific variables. I learned it both ways, so just keep that in mind. So when we talk about activation specific variables, really what we're talking about is just any kind that we normally see, right? In the example here, it's a ML function called days to ms, which is just giving us the milliseconds for a given set of days, right? And then it takes in a parameter days. And then inside of the let block within the function, we define three other variables: hours, minutes, and seconds. And then we use those to define, to set up the number of seconds in those days, right? And then we're going to use seconds in the in part of the let block to multiply by 1,000. So the interesting thing is hours, minutes, seconds, and days are all activation specific variables, right? They're just dynamically allocated as the function is called. So we also need to know that for block constructs, right? So if we think about the let block, that contain code, there's an activation for that block. That activation of the block is the lifetime of that execution of the block is tied to the activation of its function in which it exists. So a variable can be specific to an activation of a particular block within a function. This gets into nuanced how you want to set up these what we'll call activation records shortly here, and whether or not you want to have nested ones, or if you want to consider that just the fact that variable is only available at the given time that we're in the block. Lots of different things can be handled here. But when we look at the specific version of the factorial function that we see here, what we actually can think of is that we have n is defined as a part of the function itself, right? It's a parameter. But then we have inside of the let block within the function, we create a new variable b, right? B is an activation variable specific to that particular block, whereas n is activation variable specific to the enclosing function's activation. So keeping all that in mind, now that leads us to a problem. If we have separate records for each of these, how do we deal with that? And we'll talk about that shortly here. So there are also other different lifetimes for variables, right? And I alluded to this when I talked about static versus dynamic earlier. So almost all imperative languages, as it says here, have a way to declare a variable that is bound to a single memory location for the entirety of the runtime, right? So if we think about this is basically what we'll call a global variable. In Java, these are if we think of the lifetime of a class, right, as it's once it's loaded into memory by the Java runtime, and if it has static variables, those are then available for the entirety of the run, and unless their value is changed, there's no specific version of those, right, per object of that class. It's only to that class. And furthermore, we can actually have static classes themselves. So the in C here is what we're looking at. If we declare a variable outside of all other functions, that variable is effectively global and exists at load time rather than at runtime, and its value can be accessed. So what we're saying here is that its memory location is set by the loader rather than by the runtime environment, if that makes sense. Whereas all the dynamic ones, their memory locations are allocated as needed during the runtime of the system. So then we have, so we have to understand, right? We've talked about scope. Scope is where, when are the variables actually visible, and versus lifetime, right? So most variables with local scope have activation-specific lifetimes, typically by default, although we can get around that, and we'll talk about that shortly here, meaning that the second that they come into scope, when their scope ends, they usually are no longer visible. They don't exist anymore. That's not always true, but the scope and the lifetime are not necessarily the same thing, because although it could go out of scope, the variables and things like that can still be in use. And so we have to think about how that will be, and we'll talk about that shortly here. But when it comes to, for example, this value here, we can actually state that the int count, right, in the next count method, we define it as static. So it becomes a statically allocated variable, and thus its lifetime is different than its scope, right? The lifetime of count will exist, but its scope is only within the next count function. So we can get around this, and similarly, you can do this in languages such as Ruby and Python, and I don't think you can do this in Java. But regardless, there's all sorts of other lifetimes of variables. There's object-oriented languages use the lifetime of fields are defined as are associated with the lifetime of the object in which they're contained. Languages have variables whose values are persistent, right? So if you can actually have programs that can have multiple runs, and the variables that they use can actually be accessed across all those executions, as if allocated during the first execution and does not stop being allocated until the last execution is run. I'm not aware of any languages that can do that personally, but we also can think of variables across multiple threads, right? That's another way of thinking of things. In Java, we can define variables that are transient versus volatile, and that has different meaning for how they're allocated when you talk about a multi-threading or a concurrent programming situation. But today we're only going to focus on these activation specific, or we'll say function defined variables. So this gets us to the concept of the activation record, right? So when we implement a language, the underlying language system that's going to execute programs written in that language, we have to have some way of handling the allocation of memory when functions are called, right? And that not only is the allocation of memory for the function, but also allocation of all of its variables, and such that we have enough space for the actual values that they need, right? And then the activation record will also need to contain information like the return address. So if one function called another, that when the second function is finished, it has to return back to the point in time in which it was called. So we actually have to know where that is so that we can actually maybe there's a return value that it has to provide back to the caller if there's an assignment happening. And then we also need to potentially link back to the calling function's activation record in order to access other information, like, for example, values of variables that were used, or, for example, if you're inside of an object-oriented system, you might need access to the containing classes, variables. So there's a lot of information that needs to be handled as a part of this activation record. And so furthermore, we also, as we alluded to earlier, we might have the issue of dealing with inner blocks of a function, right? The activation records associated with those, because blocks themselves can define their own local variables. So there's all different sorts of ways of dealing with this, right? And there's different possibilities for how we might handle the block activation record. We'll show what an activation record looks like shortly here. So now, if we create blocks within there, what we could do is, with knowledge of the actual function definition, we can pre-allocate the amount of memory necessary for the function's activation record in totality, right? Except, what if some of these blocks are not necessarily always accessed, right? What if there's an if structure surrounding them so that they're partially activated, they're only activated in certain conditions, for example, or if there's a loop structure surrounding them, which is going to potentially cause them not to actually be executed. So we have certain issues with that. What we can do is we can actually dynamically allocate as necessary by extending the function's activation record when the block is entered. So that and then remove that piece and free up that memory as once the activation record is closed, right? So furthermore, we can also just wholly create separate block activation records that are linked, that link back to the owning function's activation record, or the outer block, if you will. So we'll talk about the first method, which is where we're going to pre-allocate all of it at once. And so I'm going to stop here, and I'll start the next video